today's video, we are going to see section 1.5 which deals with products and quotients. So we will see basically four rules which are the product rule, quotient rule, reciprocal rule and integer power rule of differentiation. So first consider two functions f of x and g of x. Okay. So the product of the functions fg of x is defined as f of x into g of x, and also the quotient of f by g of x is defined as f of x divided by g of x, where g of x should not be equal to 0. So that's how we define the product and quotient of two functions. And when we are going to deal with the derivative of the same, say suppose we are considering fg the whole dash of x, and suppose if we are considering f by g the whole dash of x. So when we are dealing with these two different differentiations, we need two rules. So that's how we are coming into the product rule and the quotient rule. So in order to understand it further, suppose if our function f of x is equal to x cube, you have an example 1, f of x is equal to x square and g of x is equal to x cube. So how will we define fg of x? Fg of x is defined as f of x into g of x. That means fg of x is equal to x square into x cube in this example. That means x raised to 2 plus 3, which is equal to x raised to 5. Okay, we obtained fg of x. Now consider fg dash of x. That means the derivative of fg of x. So that is equal to, we know that fg of x is equal to x raised to 5. So we know the rule that d by dx of x raised to n is equal to n x raised to n minus 1. So with that equation you get fg the whole dash of x is equal to 5x raised to 4. Okay, now calculate f dash of x. You know that f of x is equal to x square. So f dash of x is equal to 2x. Similarly, g of x is equal to x cube. That means g dash of x is equal to 3x square. Right. Now just multiply f dash of x into g dash of x. So you get 2x into 3x square, which is equal to 6x cube. So you can identify that fg dash of x is equal to 5x raised to 4. F dash of x into g dash of x is equal to 6x cube. So here we can say that fg dash of x is not equal to f dash of x into g dash of x. That is the concept which example 1 gives. So this is a counter example to prove that fg the whole dash of x is not equal to f dash of x into g dash of x. So how will we find the derivative of the product of two functions? So what will be fg dash of x? So that makes us to go to the product rule. So suppose if you have a function f of x and g of x and you are dealing with the product f of x into g of x, and you have to find the derivative. So how you will find the derivative? Fg the whole dash of x is equal to, first you write the function f of x as such, then multiply it with the derivative of g of x, g dash of x, plus first you write the derivative of f of x into g of x, or you can say that d by dx of uv is equal to u into derivative of v plus the derivative of u into v, or you can write this is the same as uv the whole dash so you get here uv the whole dash is equal to u into v dash plus v dash into u. So you can use any of the three forms of the product rule. So hope you are now familiar with the product rule, and we can solve some examples using this product rule. So first, in example 2, we have to verify the product rule for f and g in example 1. So in example 1, f of x was x square. So let's write here f of x is equal to x square, and also g of x was given in the example 1 as x cube. Okay. So we already found out that fg dash of x is equal to 5x raised to 4 from example 1. Okay, now you have to find and verify that the product rule is giving us the same answer for fg dash of x. So you are finding the right hand side of the product rule. So in the solution, we know that we have to verify the product rule. So we have to find the LHS, right? You have to find the LHS. You have to find the RHS. In order to verify, you have to find the LHS, you have to find the RHS, and then you have to say that LHS is equal to RHS. That is how you verify an equation. So here in the LHS, you have fg dash of x. So you have fg the whole dash of x, which was calculated earlier. So you get it to be 5x raised to 4. Okay, and RHS is nothing but f of x into g dash of x plus f dash of x into g of x, right? So that is equal to, what is f of x? F of x is nothing but x square. Then g dash of x will be, g of x is x cube. So g dash of x will be 3x square, right? Plus f dash of x will be 2x. G of x is x cube. So in total you get, when you multiply here, you get 3x raised to 4 plus 2x raised to 4, which is nothing but 5x raised to 4. So you have verified LHS is equal to RHS. So the product rule is verified here. So that was example 2a. And the next example is verify the product rule for f of x is equal to x raised to m and g of x is equal to x raised to n, where m and n are natural numbers. So let's do the B part of our question. So the B part gives us, basically we have f of x is equal to x raised to m and g of x is equal to x raised to n, where m and n are belonging to the set of natural numbers. Okay. Then you have to find the LHS. LHS of the product rule is nothing but fg dash of x. Okay. For that, to find that, first you have to find something else. You have to find fg of x. Fg of x is nothing but x raised to m into x raised to n. So you get x raised to m plus n. And then fg the whole dash of x by the rule d by dx of x raised to n is equal to n x raised to n minus 1, right? So here you will have m plus 1, m plus n into x raised to m plus n minus 1. So that will be fg the whole dash. So you have in the LHS m plus n into x raised to m plus n minus 1. So what is the RHS? RHS of the product rule is f of x into g dash of x plus f dash of x into g of x. So you have to find f dash of x here. What is f dash of x? f dash of x will be m into x raised to m minus 1. Similarly, g dash of x will be n into x raised to n minus 1. So give all those substitutions in the RHS. So you have f of x, which is x raised to m, g dash of x, which is equal to n into x raised to n minus 1, plus f dash of x is nothing but m into x raised to m minus 1 into g of x is nothing but x raised to n, and when you solve you get x, you have n, the constant there, and then you have x raised to m plus n minus 1 plus the constant m into x raised to m plus n minus 1, because you know x raised to a into x raised to b is equal to x raised to a plus b. That is the property we use here. We know that x raised to a into x raised to b is equal to x raised to a plus b. Or okay, so that is what we have used here. So finally, you have the same powers of x. So you can take the constants like this, m plus n into x raised to m plus n minus 1, and therefore we obtained LHS is equal to RHS, and we have verified the product rule. Product rule is verified. So when a question of verification is asked, we have to do like this. So we have to also prove the product rule. So how will we prove the product rule? So for the proof, so we have to show that we have to show? We have to show that fg the whole dash of x is equal to f of x into g dash of x plus f dash of x into g of x. This is what we have to show. So for that we are taking the LHS. Again, we are rigorously showing mathematically, not just by an example. We are showing it in general how this is valid. So we are taking the LHS. LHS is equal to fg dash of x naught. Say we are taking an arbitrary x naught for an arbitrary point x naught. Say. So by the definition of derivatives, we know that this is equal to limit delta x tends to 0 fg of x naught plus delta x minus fg of x naught the whole divided by delta x. So that is what which is written here, and that is equal to limit of delta x tends to 0. Use the definition of the product. So you get that is equal to f of x naught plus delta x into g of x naught plus delta x minus f of x naught into g of x naught the whole divided by delta x. So that is neatly shown here. And now we have to get an expression for the numerator. We are taking the numerator now, and we are going to express it in some other terms. So for that you are going to consider a geometry. Okay, suppose the point, suppose if the length sitting here this much is denoted by f of x naught, okay, and the whole length from here to here is equal to f of x naught plus delta x. So if we are taking the point here, we know that the small portion here, this length will be f of x naught plus delta x minus f of x naught, right? Now similarly here, suppose the length from here to here is g of x naught. Okay, and the whole length is g of x naught plus delta x. So the small length sitting here will be g of x naught plus delta x minus g of x naught, right? Now since this is f of x naught and this is g of x naught, the area of this section, the gray section, will be f of x naught into g of x naught, right? And the whole area will be f of x naught plus delta x into g of x naught plus delta x. And we can consider these three sections too. We can find their the area of region 1 is equal to, how will we find this area? So till this much the length is f of x naught, okay, and this much will be g of x naught plus delta x minus g of x naught, okay. And also area of region 2 is equal to f of x naught plus delta x minus f of x naught into g of x naught plus delta x minus g of x naught. And area of region 3 is equal to f of x naught plus delta x minus f of x naught into the region here. This much length will be g of x naught into g of x naught. So this is in total what we get, g of x naught. Okay, so in total, we know that area of the bigger rectangle. Area of the bigger rectangle is here. Area of larger rectangle. So that will be equal to, the whole length will be f of x naught plus delta x into g of x naught plus delta x. Okay, so in order to find the area of the unshaded region, you have to subtract the area of the shaded region from the total region, right? So you have here the area of shaded rectangle will be equal to, that is equal to f of x naught into g of x naught, right? So here we can infer that area of unshaded region, area of unshaded region is equal to area of the bigger rectangle minus area of the shaded region, right? So it can be written as f of x naught plus delta x into g of x naught plus delta x minus f of x naught g of x naught. So you can understand that this is the numerator we are talking about, this numerator, okay. And this can also be written as area of the first region plus area of the second region plus area of the third region. So I am just going to write area of 1 plus area of 2 plus area of 3. Both are the same. So instead of the numerator, this we can write it as the sum of the three terms, right? So that is what we are going to do. So here we have the numerator. We are talking about f of x naught plus delta x into g of x naught plus delta x minus f of x naught into g of x naught is equal to the sum of the three areas which we had written here. Okay. And then what you have to do, instead of this numerator, you will write the sum of the three terms and then apply limit delta tends to 0 and divide it by delta x. So that is what which is written here. Limit delta x tends to 0, the first term divided by delta x plus the second term divided by delta x plus the third term divided by delta x. And by the properties of limits, we know that here delta x is the variable which tends to 0. So g of x naught need not, it is actually a constant. So we can take the g of x naught out the limits. And also limit of a function plus another function is equal to limit of the first function plus limit of the second function plus limit of the third function. So these two properties are used here. And also in the second term, we know that f of x naught doesn't have any delta x, so it can be treated as a constant and it is taken outside the limits. And in the third term, it happens like this. And in the first term, we can understand that this term is actually the definition of f dash of x. This one, this term, this is nothing but the definition of f dash of x, and also this is nothing but the definition of g dash of x. So this is g dash of x, g dash of x naught. This is nothing but f dash of x naught. So you can have them written like that. Um, so this is actually f dash of x naught multiplied by g of x naught and f of x naught multiplied by g dash of x naught plus the third term. Okay. Now we are taking the two terms, the first two terms. You from that you obtain f dash of x naught, g of x naught plus f of x naught into g dash of x naught. Okay. Now we have to think about the third limit. Okay. So you know that this third limit is coming from the small rectangle here. Okay, this is the third term. There is just a rearrangement. We had taken 1, 2 and 3 and they have labeled it differently. Okay, so this rectangle actually represents the third term sitting here. Okay, so we can say that when this delta x is tending to 0, when delta x is tending to 0, this rectangle here or the square sitting here is becoming smaller and smaller and smaller, right? So it will become like this, going like this, going like this, and it will tend to just a point. That means that limit, the third limit here, which represents that smaller rectangle, will tend to 0. So at last you are getting limit delta x tends to 0 of f of x naught plus delta x minus f of x naught divided by delta x into limit delta x tends to 0 g of x naught plus delta x minus g of x naught, which is nothing but this one. Okay, so that is actually tending to 0, and this is because we know that the function g is continuous. Here it is said that g is continuous. Why? Because g is having derivative. Having derivative will mean that g is continuous at x naught. We had proved that implies g is continuous at x naught. So you can just rearrange this term. So the third term can be rearranged like take this as the first term and this as the second term, and then you know that limit of AB is equal to limit of A into B. That's what which is written here. So limit delta x tends to 0, the first term into limit delta x tends to 0, g of x naught plus delta x minus g of x naught. And since g is continuous at x naught, this term will be equal to 0 because it is continuous at x naught. So you have the third term to be f dash of x naught into 0 equal to 0. So you can either talk about in the geometrical way, saying that the smaller rectangle will tend to 0, the area tends to 0, or you can use the properties of the limits and the continuity of g to say that the third term is 0. So finally what we obtain is that the product rule is officially proved. That is, we have proved that what we have proved, whenever you have two functions f and g, then f of fg the whole dash of x is equal to f of x into g dash of x plus f dash of x into g of x. This is a very fundamental and important rule which you have to keep in mind while dealing with differentiation and working out problems related to it. So you can see example 3. Example 3, using product rule differentiate this term. Okay. So you can use two types of methods. First method is use the product rule. Then they have asked check your answer by multiplying out first. So the first method is here. First method, derivative of x square plus 2x minus 1 into x cube minus 4x square. So you take the derivative of the first term d by dx of x square plus 2x minus 1 into the second term. Okay, derivative of the first term into the second term plus the first term into derivative of the second term. So that's what we have done, the product rule by product rule. So you get this is equal to 2x plus 2. See, the derivative of x square plus 2x minus 1 will be 2x plus 2 into x cube minus 4x square plus x square plus 2x minus 1 into derivative of x cube minus 4x square will be 3x square minus 8x. Then simplify it. Multiply open the braces, then simplify to get 5x raised to 4 minus 8x cube minus 27x square plus 8x. Okay, this is our first method. So we obtained the derivative of the function given. Now method 2, second method. Second method is we are going to first of all multiply the two terms. So when you multiply, you get this is equal to x raised to 5, and simplifying you get this is equal to x raised to 5 minus 2x raised to 4 minus 9x cube plus 4x square. Okay. And you have to take the derivative of this term. When you take the derivative, you get 5x raised to 4 minus 8x raised to 3 minus 27x raised to 2 plus 8x. And you can understand that what we obtained by the first method and the second method is the same. So what is this actually? This is d by dx of x raised to 5 minus 2x raised to 4 minus 9x cube plus 4x square. See. So you got both of them to be equal. Now example 4 asks us to differentiate x raised to 3 by 2 by writing x raised to 3 by 2 as x into x raised to 1 by 2. Root x is x raised to 1 by 2. So you have to differentiate it. So for that, first we are writing the derivative of x is 1 and derivative of root x is 1 by 2 root x. So you have to keep this in mind. We had proved the same in the earlier sections. So by the product rule, d by dx of x raised to 3 by 2 is equal to d by dx of x into root x, which is equal to the derivative of the first function into second function plus first function into derivative of the second function. So you get derivative of the first function is 1 into root x plus x into derivative of the second function is 1 by 2 root x. So you get x plus 1 by, you can cancel this out, right? So when you cancel, you get root x there. So you get root x plus 1 by 2 root x, which is nothing but 3 by 2 root x. So this is the first method by product rule. The second method is second method is just straightforward, apply d by dx of x raised to n is equal to n x raised to n minus 1. So that is what we have written here. D by dx of x raised to 3 by 2 is equal to 3 by 2 into x raised to 3 by 2 minus 1, which is x raised to 1 by 2. So you have this is equal to 3 by 2 root x. So you have verified that using the first method and using the second method, what you obtained is the same. That's what we have been asked by example 4. And the next comes how to deal with quotients. So for quotients, you have two functions f of x and g of x. So h of x is equal to f of x by g of x, where f and g are differentiable at x naught. And when we are talking about quotients, always emphasize the fact that the denominator at x naught is not equal to 0. Okay. Now we are assuming that derivative of h exists at x naught, that is h dash of x naught is existing. So since h of x is equal to f of x divided by g of x, we can write f of x is equal to g of x into h of x, right? Okay, so that means we can find f dash of x naught. F dash of x naught is equal to, using product rule, the derivative of the first function, so that is g dash of x, into the second function plus first function into derivative of the second function. Okay. Now solve for h dash of x naught from here. So here you get, this will imply g of x naught into h dash of x naught is equal to f dash of x naught minus g dash of x naught into h of x naught. So you get h dash of x naught is equal to f dash of x naught minus g dash of x naught into h of x naught divided by g of x naught, which is written here. Okay. And instead of h of x naught, we can substitute by f of x naught divided by g of x naught. Right. And then you simplify it and you will be getting f dash of x naught into g of x naught minus f of x naught into g dash of x naught divided by g of x naught the whole square. So this gives us the quotient rule, which is nothing but if f of x and g of x are two functions, the quotient f of x divided by g of x, where g of x is not equal to 0, we will get f by g dash of x is equal to the derivative of the first function into the second function minus first function into the derivative of the second function divided by second function the whole square, or d by dx of u by v is equal to derivative of u into v minus u into derivative of v divided by v square, or we can write u by v the whole dash is equal to u dash into v minus u into v dash divided by v square. So this is the quotient rule, which is also very important and you have to keep in mind whenever you are dealing with quotients and differentiation. So let's solve for the first example. Differentiate x square by x cube plus 5. By quotient rule, we know that f of x is equal to x square, g of x is equal to x cube plus 5. So d by dx of x square by x cube plus 5 is equal to the derivative of the first function, which is 2x, into the second function, which is x cube plus 5, minus the second function, which is minus the first function, which is x square, into the derivative of the second function, which is 3x square, the whole divided by the second function, which is g of x the whole square, x cube plus 5 the whole square. Then simplify the same to get, you just open the braces, you get that to be equal to 2x raised to okay, so you have here 2x and you have here x cube. So you can take out x as a common factor out. So you get, if x is taken out, you have inside 2 into x cube plus 5, and x is already taken out. So you have there x into 3x square the whole divided by x cube plus 5 the whole square. Okay, so you get that to be equal to x into 2x cube plus 10 minus 3x cube the whole divided by x cube plus 5 the whole square. And here you have 2x cube minus 3x cube. You can simplify that to be equal to minus x cube plus 10. So this is the final answer. Similarly, find the derivative of h of x is equal to 2x plus 1 divided by x square minus 2. So how do we do? For the first function will be 2x plus 1 f of x. The second function will be x square minus 2. Then apply the quotient rule. Simply apply the quotient rule. So h dash of x is equal to derivative of the first function will be 2 into second function minus the first function into derivative of the second function, which is 2x, the whole divided by denominator square. So simplify it and you get the answer here. The next is find the derivative of root x divided by 1 plus 3x square. So for that, d by dx of root x divided by 1 plus 3x square is equal to 1 plus 3x square into derivative of the first function, which is 1 by 2 root x minus the first function into derivative of the second function, which will be 6x the whole divided by 1 plus 3x square the whole square. And simplify, you get the answer to be equal to 1 minus 9x square divided by 2 root x into 1 plus 3x square the whole square. So in the same manner we proved the product rule, here also we have the proof of the quotient rule. So in order to prove the quotient rule, we have h of x. So what we are going to do is, here we are going to show that f by g the whole dash of x is equal to f dash of x into g of x minus f of x into g dash of x the whole divided by g of x the whole square, where g of x is not equal to 0. Fine. So this is what we are going to show. So we are treating this f of x by g of x. F of x by g of x is equal to h of x. We are assuming it in the proof. Okay, so we have assumed it here, and we are finding the derivative of h dash of x. So h dash of x naught, by the definition of derivative, we have that to be equal to limit of delta x tends to 0, h of x naught plus delta x minus h of x naught divided by delta x. Okay, then apply the definition of h of x. So instead of h you have f by g, and when you give the definition, you get that to be equal to limit of delta x tends to 0, f of x naught plus delta x divided by g of x naught plus delta x minus f of x naught divided by g of x naught the whole divided by delta x. And then you rearrange, you get f of x naught plus delta x into g of x naught minus f of x naught into g of x naught plus delta x divided by g of x naught into g of x naught plus delta x into delta x. So in the numerator you will have an f of x naught, g of x naught, and minus f of x naught into g of x naught. We are going to add and subtract. We know that that is equal to 0. So you are going to add and subtract the same in the numerator. That is, we are going, see, the guys sitting here. We know that both of them will add up to 0. So it doesn't make any difference. Okay, so you are including them in the numerator. And then what you do is you're going to take the denominator out, excluding delta x. Okay, 1 by g x naught into g of x naught plus delta x into what you have in the new, what you have, the rest will be f of x naught plus delta x minus f of, you're taking this f of x naught, divide by delta x into g of x naught, and then you take this one, uh, g of, you take this term and this term. Okay, so you club the terms, this one and this one, and then you club the terms this term and this term, and then rearrange like this. Okay, you can, when you write it down, you will get it easily how this will reach here. And then you know that delta x naught is tending to 0, so you take this term like this, and you are applying limits in limit of this function into limit of this function, and then apply limit of a plus b is equal to limit of a plus limit of b to get this term to be equal to, or I can write it like this, limit of delta x tends to 0, 1 by g of x naught into g of x naught plus delta x is the first term, into limit delta x tends to 0, the second term, f of x naught plus delta x minus f of x naught divided by delta x into g of x naught minus f of x naught into g of x naught plus delta x minus g of x naught, the whole divided by delta x. So this is what you obtain from here. Limit of a b is equal to limit of a into limit of b. And again you can apply the property that g of x naught will be a constant here. So you get g of x naught into limit delta x tends to 0, 1 by g of x naught plus delta x, and then you split the limits as sums and take constants out. So here you have g of x naught you can take out, then you have limit delta x tends to 0, f of x naught plus delta x minus f of x naught, the whole divided by delta x, minus, here you can take f of x naught out because x naught is doesn't have delta x. So you have, this is equal to limit delta x tends to 0, g of x naught plus delta x minus g of x naught, the whole divided by delta x. And when you find that this is nothing but, this is nothing but f dash of x naught, and this is nothing but g dash of x naught. So you finally get 1 by limit delta x tends to 0, this term into this term into the term f dash of x naught into g of x naught minus f of x naught into g dash of x naught. And when delta x tends to 0, this term is nothing but 1 by g of x naught. That is what is written here. And substituting everything, finally what you obtain here is h dash of x naught is nothing but f dash of x naught into g of x naught minus f of x naught into g dash of x naught divided by g of x naught the whole square. So what is h dash of x naught? H dash of x naught is nothing but f by g the whole dash of x naught. So you have proved the quotient rule like that. Now the next rule is called the reciprocal rule. Reciprocal rule says that if we have a function g of x and then its reciprocal 1 by g of x, where g of x is not equal to 0, keep that in mind, this is very important. Then 1 by g dash of x is nothing but minus g dash of x into g of x the whole square, or d by dx of 1 by u is equal to minus 1 by u square into du by dx. So this can be derived actually from the quotient rule very easily. We know that quotient rule is like this, or quotient rule says that f by g the whole dash of x is equal to f dash of x into g of x minus f of x into g dash of x the whole divided by g of x the whole square, right? So here f is 1, right? Here the function f of x is 1. When f of x is equal to 1, what you obtain is 1 by g the whole dash of x is equal to 1 into g of x no, this is f dash of x. So constant functions will have the derivatives to be 0, so this will be 0 into g of x minus f of x is 1, g dash of x you write it the same, the whole divided by g of x the whole square. So that is nothing but minus g dash of x divided by g of x the whole square. So this also you have to keep in mind. This is also very important rule. Let's see example 7. You have 1 by x cube plus 3x squared. So if it is given and you have to find the derivative, what you have to do? You have to write 1 by the term square. Minus 1 by the term square first. Minus 1 by x cube plus 3x square the whole square first, and then take the derivative of the term d by dx of x cube plus 3x square. So you get that is equal to minus 3x square plus 6x divided by x cube plus 3x square the whole square. So that's how you arrive at the answer here. And for the second question, 1 by root x plus 2. So how you get 1 by root x plus 2? That is equal to, this is the question. So you have to take minus 1 by the term square, minus 1 by root x plus 2 the whole square into d by dx of root x plus 2, which is nothing but, this is equal to minus 1 by root x plus 2 the whole square into d by dx of root x plus 2 will be 1 by 2 root x. So finally you get minus 1 by 2 root x into root x plus 2 the whole square. So that's how we get the same. Now suppose if we are having the function x raised to minus k, say our function is uh, f of x is equal to x raised to minus k. So it can be written as 1 by x raised to k, right? So suppose we are finding the derivative of it. See, d by dx of 1 by x raised to k is equal to, use the reciprocal rule, minus 1 by the term square x raised to k square into d by dx of x raised to k. So you get minus 1 by, when you have x raised to k, x raised to k the whole square, you have x raised to 2k, because x raised to m, the whole raised to n will be x raised to mn. So using that you have minus 1 by x raised to 2k into k x raised to k minus 1. Finally, when you rearrange, you get minus k into x raised to minus k minus 1. So you have to recall x raised to m into x raised to n is equal to x raised to m plus n. Similarly, x raised to m minus n is nothing but x raised to m by x raised to n. So you have to use all these rules here to finally obtain that. Okay, the next is the integer power rule. The integer power rule says that for any positive, negative or zero integer, d by dx of x raised to n is equal to n x raised to n minus 1. So when n is strictly less than 0, that means you are taking negative values, x must be not equal to 0. So that is the only condition which is given. So the first question is, this is the one which we had already proved, but it is actually deriving from the reciprocal rule as we said earlier. So we can in general say for any positive, negative or zero integer. So differentiate 1 by x raised to 6. So you get d by dx of 1 by x raised to 6 is equal to d by dx of x raised to minus 6, which is equal to minus 6 into x raised to minus 6 minus 1. So you get minus 6 into x raised to minus 1. Now differentiate the first one a, which is 3x raised to 4 plus 2 by x minus 5x raised to 3. So you use all the rules. Okay. So first you have to split them up. Right, like this, take the constants out. Then you have to apply the derivative. First the derivative of x raised to 4 will be 4x cube. Here derivative of x raised to minus 1 will be minus 1 into x raised to minus 2. Right. And x raised to minus 3 will have the derivative minus 3 into x raised to minus 4. Then write it in the simplified form. You get 12x cube minus 2 by x square plus 15 by x raised to 4. Now for b, you have the function in the denominator to be x square plus 3 into x square plus 4. So for finding this one, you can use the reciprocal rule. We know the reciprocal rule says that d by dx of 1 by g of x is equal to minus 1 by g of x the whole square into g dash of x, or d by dx of g of x. So you have to find this g dash of x. So here our function in the denominator is this. So you have to find the derivative of. Here we have to find d by dx of, just renotate it by f of x. That is equal to minus 1 by f of x the whole square into f dash of x. This is what you have to find. So you have to find this first. So f dash of x is equal to, how to find? You can use the product rule there. First the derivative of the first function into the second function plus the derivative of the second function into the first function. So you obtain 4x cube plus 14x. Then by the reciprocal rule, d by dx of 1 by f of x will be equal to minus 1 by f of x the whole square into f dash of x. Substitute that to obtain this. In example 10, we derive the reciprocal rule from the quotient rule, which we already discussed. How did the reciprocal rule came? we had obtained it. So these are in total the differentiation rules which you have to be very thorough with, so that you can do the questions which require the product rule, reciprocal rule, quotient rule, and the integer power rule. So you have to be very thorough with all these derivatives. The derivative of bx plus c is equal to b. The derivative of ax square plus bx plus c is equal to 2ax plus b. D by dx of u plus v will be du by the derivative of u plus derivative of v. D by dx of k into u will be k into derivative of u. D by dx of x raised to n is equal to n into x raised to n minus 1. D by dx of the polynomial sitting here, this is a polynomial, that is equal to ncn x raised to n minus 1 plus etc. plus 2c2. This is nothing but n into Cn. Cn is the constant sitting here, or you can say if this is A, call it A, A2, A1, A0. So you have N x raised to n minus 1 plus etc. plus 2A2 x plus A1. Okay. D by dx of ub is equal to the product rule. The derivative of the first function into second function plus first function into derivative of the second function. D by dx of u by v is equal to the derivative of the first function into second function minus first function into derivative of the second function divided by second function the whole square. D by dx of 1 by v is equal to minus 1 by v square into dv by dx. So that's how we end up with the rules, and you have to solve all the questions that are in the exercise of section 1.5, and you have to submit, you have to complete all the lecture notes, and also submit when you are asked to submit as assignment, submit all the worked out solutions of the exercises here from 1 to 56. You'll have time till next Tuesday. So thank you for watching out the video, and please do have a thorough understanding of all the rules, because these are all very important as we move forward in the other modules too. So thank you.